Uh, Ladies and gentlemen, welcome to the sixth and final Ulster Beekeepers Association winter webinars. We're delighted, in fact, to have you all here. My name is John Hill. I am chairman of the Ulster Beekeepers Association. And as I say, we decided to run this set of webinars instead, in fact, of our conference, which was normally run at this time of the year. And we've been absolutely delighted that so many people have joined us from right across the globe for these webinars. I would say I'd like to thank Thorn for their very generous sponsorship to us for helping us to run this webinar this evening. This is the second one that they sponsored with Dr. Pettis. And indeed, again, it says, well, I'm delighted really that this evening's lecture is by Dr. Jeff Pettis, who is presently the president of Apimondia, which is the worldwide federation of beekeeping associations. Dr. Pettis was a research leader at the USDA ARS Bee Research Laboratory in Beltsville, Maryland. Now, for those of you who don't know where Beltsville is, it's about 25 miles north of the Capitol in Washington, where a rather significant event happened a few weeks ago. And indeed is the center of bee disease diagnosis in the United States. Dr. Pettis is now an independent consultant, and he's focused on improving colony health by limiting the impact of pests, diseases, and pesticides on honeybees. His research areas include integrated pest management techniques to reduce the impacts of parasitic mites and diseases, effects of pesticides and pathogens on queen health and longevity, host-parasite relationships, and bee behavior. Dr. Pettis has served really on several international committees, and as I said earlier, he is president of Apimondia, and he's attended meetings at the World Organization of Animal Health, which is called the OIE. He is frequently interviewed by the media, and his opinions on worldwide pollinator declines and honeybee health. He's received undergraduate and MS degrees from the University of Georgia and his doctoral degree in entomology from Texas A&M University in 1992, which only goes to prove that he's really quite smart. So really, without further ado, I would really like to welcome you to the sixth and final webinar by Dr. Pettis. Please, if you have questions, could you please put them into the Q&A facility on your screen. Thank you very much.
Hi, excuse me. Hi, Dr. Jeff Pettis. Today we're going to talk about queens and queen health and some of the things that you can do in your own colonies to recognize when you might have a queen problem and how the queen affects colony productivity, et cetera, et cetera. So we're going to cover quite a few aspects of queen biology and recognizing queen problems in the hive. And then at the end, I'll try to answer some questions if we have time. So I'm going to start and share my screen here, and we'll get to the presentation. There we go. All right, so queen health and colony productivity. The two are linked, of course. In most honeybee colonies, there's only a single queen. But in fact, if you are a careful beekeeper and you look through your colonies, you'll find out that about 5 to up to 10% of the time, you actually have two queens in a colony. And that's because as a queen ages, they may supersede her, replace a failing queen. And when they do that, often the two queens overlap. So my professor, Dr. Bill Wilson, did a study, and he kept looking through colonies after he found the first queen. I think he found it almost 7% of the colonies, he found a second queen. So, which brings up a very good question. When we're going to do a colony inspection, do we really need to see the queen? The short answer to that is no. You can look for eggs and other signs that'll tell you that, in fact, the queen is present. So if you're a beginning beekeeper and you're getting obsessed, you've been looking, you're going into your colonies and looking for the queen and you can't find her, don't worry about it. Learn to recognize those signs and symptoms that the queen is there. One good indication is fresh eggs. So, and eggs are hard to see as well, but if you see eggs, you can be almost assured that she's still there. Eggs last 3 days. But the other way is learn to recognize the sound of a queenless colony. A colony that doesn't have a queen will really begin to buzz when you open it. And it's very distinctive. Once you learn it, it's kind of like American foulbrood smell. Once you learn the American foulbrood smell, you won't forget it. Same with queenlessness. If you hear that sound, you can bet for sure that they're queenless, with the exception, of course, there's always exceptions, right? The exception being if you've got a new split or a new queen being introduced, sometimes they're not quite used to her and they will make almost a queenless sound when they're not fully acquainted with that queen. So, but again, you can know that the queen is present pretty much by whether they're behaving normally and whether there's eggs present. So let's move on from there. So why are we so interested in queens, or why in queen health and queen quality? When beekeepers are losing colonies are dying, they often identify queen loss as one of the major drivers of why those colonies died. And there's some references there in the bottom. And I'll show you some data from a Canadian survey where they ask beekeepers, why are your colonies dying? Or why did you think your colonies died? We've done the same in the US and we get similar kinds of answers. Queen issues come up as the number 1 or 2 reason why they believe colonies die in many of our surveys. So this is just data from Canada, and I thank my Canadian colleagues for sharing it with us. So if you look down the side, you've got the provinces: Newfoundland and Labrador, Prince Edward Island, Nova Scotia, New Brunswick, Quebec, Ontario, Manitoba, Saskatchewan, Alberta, and BC. Just doing my geography there. Anyway, so that's the provinces. And across the top, the number 1 reason, the number 2 reason, number 3 reason. And as you can see, poor queens were identified as the number 1 reason in 5 of those provinces. The second one, if you look down the second and the third list, are the poor queens and poor queens. So even number 2 was, that makes seven out of the 10 provinces identified poor queens as the first or second reason that they were losing colonies. And we know that intuitively that queen problems can lead to colony loss. So if the queen fails or they fail to replace her, then that colony is probably ultimately going to die. If a queen becomes a drone layer and they can't replace her, that colony is likely to die. Okay, the outline of my talk. The first part, I'm just going to cover some basic things that you as a beekeeper can do and how to recognize queen problems in your hive. And then I'm going to go on and talk about 3 different sets of kind of experiments and some work that we've done on recognizing whether we have a failing queen problem. That's number 1. And number 2, some things about temperature and queen shipment that I've done recently. And then last, some work that I did with Canadian colleagues on heat stressing and cold stressing queens, and then looking at their colony level performance. And that's done with, again, in conjunction with Ag Canada, some of my colleagues there. So I'll show you those 3 experiments. But first, if you're going to examine your colony and you see eggs, and okay, the queen's present, perhaps they're not buzzing, what's the next thing you want to look for? Well, it's queen cells and also just the brood pattern. So we're going to talk about brood patterns and what they might mean and how they can indicate queen problems. We're going to talk about the 3 types of queen cells that are present in the colony, and then some other signs or symptoms or signals that you might get about queen health. So first, the brood pattern. What is a good brood pattern? That depends on your point of reference. I've seen some pretty lousy brood patterns, and when we do science experiments on bees, and we measure the brood pattern, we count 100 cells. So we look at a 100 cell area and we count the number of missing cells in there. If you look in this group, if you counted 100 cells, it would probably be between 5 and 10% missing cells. Now, there could have been pollen in those cells. The queen may have just skipped egg laying there. She didn't lay an egg. Or it could be that she laid something, it died of disease, and they pulled it out. There's a bunch of reasons why there are skips. But what we do know is that when you have a really good queen and the colony's in really good health, that brood pattern is completely solid. I mean, there may only be very, very few skips. So the question is, what indicates a poor brood pattern? And I don't have a specific cutoff, but I will say that if you count 100 cells, and I'll show you a grid that you can use in a few minutes, if it's more than 20% skips, that they're not sealed brood in there, you probably got an issue. Now, again, this is in the spring and summer when there's nice big brood patterns. You know that she's laid in a big brood pattern, and yet something happened or in those cells to make them skips. So that's the first thing. Obviously, disease can play an important role here, as can things like hygienic behavior. Very hygienic bees, they may be pulling out what was healthy brood, but now is infested with varroa. So I don't want to tell you that, the brood pattern is a clear indication that, the queen is failing or not. But I use about a 20% skips in that 100 cell area as a break point. It's above that, it's a poor brood pattern. What you can really count on is queen cells, the presence of queen cells. Now, the queen cells are different from queen cups, and we'll get to that in a minute. But I'm going to use my cursor here. In this upper left-hand corner, those 4 queen cells at the bottom of a frame, they're almost surely swarm cells. So the colony has gotten congested. It's probably in the spring in the northern hemisphere. In the tropics, it could be any time of the year, but they're crowded and they're going to swarm. So they rear swarm cells, nice long cells. And swarm cells can be differentiated from supersedure cells, usually by the placement on the comb, where they are, and by the number. This, let's say, is an example of a supersedure cell. I'm looking for my cursor again here. There it is. This single cell, even though it looks like it's at the bottom of the frame, because it comes out from the comb and turns down, it's kind of on a platform. It could be in the center, up in the center part of the frame, anywhere. But if they're supersedure cells, you'll only see 1 to 3 or 4 cells spread out in different parts of the comb and on different combs. Those are probably supersedure cells. Let's cover the last type of cell that you'll see in a colony. And this is more likely to be beekeeper or bear related. And that's called emergency queen cells. When we examine our colonies, we can sometimes putting the frames back and stuff damage the queen, and they will immediately begin to raise new queens when that queen signal drops off. And these are supposed to be examples of emergency queen cells. They're usually together in clusters. So like you got 2 cells here, you got 2 or 3 cells up here being formed. They select an area with the appropriate age larvae that are about 24 hours old, and they begin to provision them with royal jelly. So in emergency queen ring, they have a very short window. They've gone queenless. They now start raising queen cells, and that's why you have this clustering of the number of cells in emergency queen ring. It's because they've selected some that are appropriate age, and they begin to work in that area and provision them with royal jelly. And you'll contrast that. These are together. These swarm cells, even though they'll be pretty close together, they're not usually tied together. Here, they're almost, seems like they're always like 1 or 2 are tied almost right cell to cell. The other thing that's really distinctive is that these come out of the, for my cursor again, this comes out of the face of the comb. It's not as clear here as it would be up here. They take this cell and they bring it out and they turn it down and elongate it. So these cells are not, they don't appear as big as these swarm and supersedure cells. Swarm cells and supersedure cells are normally built on platforms. And that brings me to, what is a queen cup? Should you worry about this item here? This is a little, what I would call a queen cup. And I know because I looked at it and there's nothing in it. It's polished and clean. There's no egg or young developing larvae. Colonies rear queen cups all the time. In fact, they have them present in many places in the hive. And to me, that's just a guarantee. They're ready to go to work when they need to raise a new queen, especially for swarming and supersedure. So when you start seeing cups in a hive, don't get too concerned. If you see larvae or royal jelly in those cups, then yes, now it's a queen cell, even if it's not sealed. So again, learn to recognize the 3 types of queen cells. And in the first two, swarming and supersedure cells, the queen is still present. They're doing that queen rearing in the presence of the queen. In the last one, emergency queen rearing, they're actually rearing the queen in the absence of the queen, and that starts this rapid queen replacement cycle. So that's a good way to know if the colony is telling you that the queen needs to be superseded, then they know best. They've gotten signals that she's not performing well. What are some other signs and symptoms that you can look for as far as queen health? Well, we recommend if you have things like high chalk brood levels, or even with European foul brood, which you see pictured there in this top corner, this is European foul brood, that requeening the colony can help, and that's simply to replace the genetics. We know that hygienic stock will take care of chalk brood quite well, American foul brood, and to some degree European foul brood. So replacing a colony where the queen has, a poor brood pattern or disease brood, chalk brood, foul brood, stuff like that is a good idea. Not American foul brood. American foul brood, you should burn the combs and follow local recommendations. The other thing that we recommend, replacing the queen is when a certain colony in your apiary just is slow to build up, and you're judging that by the other colonies in the apiary. So can we always blame the queen on that? No. Could be high levels of nosema. It could be a number of things. But if you've got a colony that's really lagging behind, replacing the queen might cure that. It's kind of like when your computer doesn't work, you restart it and it clears up all the hangups it has. Same kind of thing. We don't always understand what's happening with a colony, but requeening can help in many cases. The last thing I have mentioned there is color. Is color important? Well, it might be to you, but it really shouldn't be. If you happen to be fond of Italian queens, then you'll love this color, right? If you happen to love Buckfast or Corneolans, maybe you like this color. The color of the queen really doesn't matter much unless it's just a personal preference that you have. What does matter is that you work on the best local stock that you have. So when you're considering queens to breed from, low disease incidence, good buildup, good brood pattern, things like that, and overwintering. If they've overwintered and they're still going strong, it's a good queen to breed from. All right, so that was a little bit about how to recognize queen problems and things, not extensive. The best thing you can do there is to go to workshops, work with your local beekeepers, if you're a young beekeeper, work with a more experienced beekeeper, so that when you go through your hives, you're feeling better about being able to recognize the queen, recognize queen problems, et cetera, et cetera. Okay, so now I want to switch gears. I've got 3 different kind of experimental areas I'll cover. The first was just to kind of document that in the U.S., and this was all work I did in the U.S., that there was a problem. Beekeepers were complaining that the queens weren't lasting long, and that there was something wrong with queens. So I asked them. I'm working with commercial colonies now, and I'll go through that experiment. So we asked a group of beekeepers, if you could, please send us live queens from poor performing colonies and colonies in the same apiary that are in apparently good health. And I needed the queens alive because I wanted to test sperm viability and some other things. So I asked a bunch of commercial beekeepers, and they sent me a bunch of failing queens. I'm like, so they were more than willing to give me the queens out of failing colonies. What wasn't easy to do was to get queens from colonies in the same apiary where the colony was doing really well. And I understood that. That was asking a lot. But when I went back to them and asked a second time, I said, really, I have to have that comparison. I have to have within the same apiary, I have to have queens from high performing colonies and colonies that appear to be failing. So I just had to go back and ask them again. And sure enough, then I got these paired sets of queens. The queen, the commercial beekeeper rated the colony as failing or in good health, sent them to me, and then I dissected them. And the main thing I'm going to score here is sperm viability. And I wish I'd done sperm count, but I wasn't able to do sperm count in this case. But I did sperm viability. We're going to look at that as an indicator of how well the queen was mated and sperm viability. So on the x-axis there, you have percent sperm viability. And this is from queens from the East Coast and the West Coast. So there's East Coast and West Coast. And up here, just over 70% sperm viability in the queens from apparently healthy colonies, and over 80% sperm viability in queens that were in the Western. And now this is from the same operation. Look at the queens from failing colonies. It's down about 40%, and here it's about 45%. So there's clearly a difference in reduced sperm viability in queens that the beekeeper identified as coming from failing colonies versus healthy colonies. Well, there's no cause and effect there. That's just an association. So we set out to do a number of other experiments to try to find out what this association was, whether just having low sperm viability would lead to poor colony performance, et cetera. And that's what I'll spend the rest of my time on. And also, what are some factors that could cause the loss in sperm viability? So when we think about what factors might come into play, we can think about things over here on this side, the queen rearing and mating. Then in the US, at least in parts of the world, the queens are shipped. They're mated and then they're shipped and they're put into hives. So over here, there's a number of conditions. The hive conditions might influence how long the queen lasts. Certainly this rearing part is very important. And so when we think about rearing, you think about good flight weather, healthy drones, and nutrition of the cell builders and things like that. And there's been some work done on that. There's some references down there about effects of coumaphos and other pesticides on the queen rearing process. And I'll talk about shipping here in a minute, but on the colony side, where you put that queen matters. Maybe the colony has high levels of pesticides in it. Maybe the colonies are being transported too much. It's leading to queen loss, et cetera, et cetera. Certainly diseases could come into play. So we're going to talk a little bit about that, but mostly we're going to focus now, the next part is on this shipping. Could the shipping of queens influence sperm viability? And to look at that, what we did is we placed thermocouples, small little temperature recording devices in paired shipments. So I went to the queen breeders in California and I asked them to take 20 queens, ship 10 of them by US Postal Service, and ship 10 of them by UPS. So we're taking just a group of 20 queens from the same mating group, ship 10 by US Postal Service and 10 by UPS, and we place thermocouples in there. Their sperm viability should be identical, and we're just going to monitor and see if there are any heat or cold events in that shipment. And that's the first set of data you'll see. But first we look at the little thermocouples. They're about the size of the end of your thumb, and they fit nicely within the queen cages or between the queen cages, and they record. We had them recording every 10 minutes, I think. So they're recording temperature throughout the shipment, and we can look at that data and see what happened to those queens. The methods we're going to use, and this is what we used in the other queens as well, was just a method developed by Anita Collins and colleagues in Beltsville, Maryland. And you take looking for my cursor. The drones mate with the queen early in the queen's life. She stores sperm in her spermatheca for the sperm from about 8 to 15 to 20 drones. So she stores that sperm and she uses that sperm throughout her life to fertilize the eggs. Fertilized eggs becoming workers and non-fertilized becoming drones. If you take here from the abdomen of a live queen and you take out her spermatheca, it's a one-way ticket. You have to kill the queen. This is the spermatheca on the tip of, I think, Sue Kobe's finger. And it's about the size of a small pellet, a BB, an end of a pencil. It's a very small little thing. This is a tracheal net that you remove. If the queen is unmated, the spermatheca will be clear like this. If the queen is mated, you'll see the sperm. That's the sperm you're seeing inside. So now we put that in a test tube and we pierce it and we add these two differential dyes. So we add these two dyes. If the sperm are alive, this is the head of the sperm, this is the tails here. If the sperm is alive, the head will dye green. If the sperm is dead, the dead head of the sperm dyes red. So it's really easy then, under a microscope, fluorescent microscope, to count 100 cells and say, what's the proportion of sperm that's alive? And that's all we've done. That's what we'll do throughout these experiments. But again, you have to sacrifice the queen and look in the spermatheca, and that spermatheca can contain between 3 and 10 million sperm. There's a lot of sperm in there. So there's plenty of sperm to work with, and we're going to look at sperm viability. So this is from 6 different breeders in California. There's the 6 coming across, and this is percent sperm viability. So the very first set of bars, this is U.S. Postal Service, and this is United Parcel Service. And in this one, there's a difference, 60% viability versus 82% viability. And again, they were supposed to be the same batch of queens. So then just look across the top of these other bars. In fact, they are equal. So here, the next breeder number 2, they're virtually identical, right across. So there's not much difference in these. This is the one where we saw a significant difference. And when we went back and looked at the temperature data, that particular shipment had a cold spike, and the temperature went down to 8 degrees centigrade, which is 40-something, mid-40s Fahrenheit. So again, so we're associating that decrease in sperm viability with a cold event in this case, but we've seen it being hot events in other cases. The other thing while we're on this, where do you want to order queens from this data? Obviously from breeder number 2. Breeder number 2 comes in at 90% viability, whereas look at breeder number 4. Breeder number 4 is at 60%. If you send me a note and a $20 bill, I'll tell you which of these breeders are which. No. When I do this work, you have to keep everything confidential. And I can tell you, and this is the truth, that breeder number 2, we went back, this was in the spring. We went back and sampled in the late summer. Breeder number 2 remained high. Guess what happened with breeder number 4? He went back up in the 80 to 90%. He or she went back up in the 80 to 90%. So something about the events when we sampled breeder number 4, there was something, weather or whatever, there was just not very good sperm viability in that set of queens. I point this out because beekeepers, when they buy queens, they expect them always to be perfect. Well, there's a lot that's out of the queen breeder's control. So don't always blame the queen breeder. Oh, you sent me a bunch of lousy queens. Well, these aren't lousy. These are just marginal. These number 4 queens, these are marginal. Anything above 50%, you're probably going to be okay for a year or so. This is much better. But I'm saying this because there's a lot of factors that play into raising queens and mating queens. And so anyway, but here we've linked this particular event to cold during shipment. I don't know if I've got that. I don't have the trace of that one put in this slide set, but they did do a cold dip. This is the temperature tracings, the high and the low. The high temperature for 15 different shipments, and the same 15 shipments, the low recording for that shipment. And what I want to point out is these 2 shipments got up to our upper range, 39 to 40 degrees Fahrenheit, centigrade is the upper limit. You want to keep it below 38, really, 38 centigrade. And over here, a different 2 shipments, it was these 2 shipments here, they actually recorded a cold event, which was below 10%. And when you start getting below 10% and 8%, you start getting damage to the sperm on the low end. So in these 15 shipments, we had 2 high and 2 low events. And the low events were likely due to the fact, because they were shipped in the spring, they were likely due to the fact that the heating in the plane was not sufficient in the cargo hold. That's the only thing we can associate it with, because I think it was July, and it shouldn't have been 8 degrees. It probably had to do with the altitude of the plane. But in any case, the other take-home message from this is heat kills and cold kills. Both can kill sperm. So we've got shipping can be an issue. And now we're going to look back at some of the other things. So this is, we know we need healthy drones. We've got shipping that can have temperatures, highs and lows. And then we've got hive conditions. Back up, yeah. Hive conditions, pesticide levels in the hive, shipping temperatures, things like that. I won't have time to talk about it, but there's been some great deal of work done on drones and in queens and stuff like that. Williams talked about queens exposure to neonics and how it might affect the sperm viability. And some others have done work on drones where pesticide exposure to drones can cause reduction in sperm viability. This is a paper that I published on the queens and the effect of heat and cold on queens. So it's not just one thing, it's not just shipping. Pesticides can come into play, but I don't have time to cover all that today. So I'm just going to conclude from this part of my presentation so far. It was clear that when we pull queens from what appeared to be healthy colonies and colonies in poor health, that those queens had lower sperm viability. There was an association there. And in reality, there's probably a number of things that come into play. Pesticide levels in the hive or pesticide levels during the rearing process. Shipping can play a role. If the queens are shipped, they have to be maintained at a certain temperature. And then on the other end, the mating, the rearing of the queen and the drone quality can be compromised by pesticides and weather. So there's a lot that can go on in healthy queens. Queens are failing, and I will say that pesticides can still play a role, and they do in various aspects of queen biology. And this is the part I want to close with. There's a link between poor colony performance and reduced sperm viability. We saw that in that very first set of data, but we didn't manipulate those colonies experimentally, and we only had an association. So now myself and my Canadian colleagues set out to show this experimentally. We're going to take a group of queens, heat stress, cold stress some, leave others alone, and see how they perform in the colony. So that's the last experiment that we'll do or we'll talk about. Before we go there, I'll ask you a question. There is one single thing that you can do as a small beekeeper, even as a hobby beekeeper, that I think can overcome many of the problems we're having with queens. So what do you think that one single thing is? I'm not going to tell you. No, I'm not going to tell you now. I'm going to save that to the end. At the end of my talk, I'll ask this question again. So think about it. There's one particular thing you can do to overcome a number of queen issues that we've talked about, or that can be talked about. So last set of experiments. Queen quality, that's hard to say. Thermal stress and colony productivity. Doctors Martha Guarna and Steve Pernall at Ag Canada in Alberta carried out the field component of this, and I was involved in just helping it set it up and design it and stuff like that. But it was, again, we're going to try to experimentally find out if heat or cold stress queens performed as well as non-heat or cold stress queens. And the first thing we did was just take a set of queens here's a set of queens that we dissected that hadn't been heat stressed. These are what we call our control queens, held at 25 degrees C. You can see it's almost 90% viability. Each dot represents a queen. So about 90% viability. Look at these when we held them at 42 and 4 degrees for 1 hour each. So an hour at 42 and an hour at 4 degrees, heat and cold. And you can see it's quite varied, but on average, they only had about 60% viability. And for me, I've always thought about 50% as being the cutoff. Anything below 50%, and the queen's just not going to perform very well. So these were a little above that, but let's see what the data tells us from the colonies. And again, this is just some nice photos from Dr. Guarna showing the live dead staining. So this is 100% dead. This is 100% alive, all green. And that looks like about 50%. So it's very easy to do this fluorescent staining with a good microscope and tell what the proportion of live dead is in a queen. The problem with this experiment is you have to sacrifice the queen. So how did we know what we had going into this experiment? Well, we're going to use 60 queens in the experiment. So we got 60 queens that we want to place in the experiment, 30 in each set of colonies. We had an initial 10 or 15 queens that we got in, and we measured them pre-introduction to make sure they had high viability. So we're not going to do this whole field experiment without knowing that we got a good batch of queens in. That's the first thing. And this is also just another test to verify where do we want to work in this temperature range. The 25 degrees C, that looks like about 15 dots. I'm not sure. and that's 90% viability. That's what you want. You want it there. Look, when you go to 4 degrees or 0.5 degrees, going really cold, you see that the viability drops, but it doesn't continue to drop down from here to here. That's getting quite colder, and yet the viability didn't drop down too much. The same over here at 40 or 42, and this was either for 1 hour or 2 hours. The time doesn't matter. The time was the same. They held them for probably 2 hours. At 40 and 42, there's a little bit more reduction at 42. So you see some of these dots dropping on down. But it's interesting biology. I saw this on the cold end in particular. There's immediate loss of viability. So you lose about 50% of the viability, or 40, 30, or 40% of the viability, and then it stabilizes. So what's happening in that queen? I don't know. I mean, she actually becomes comatose and still when she gets that cold. And maybe somehow, I mean, maybe she has some type of, we'll call it antifreeze within the queen that keeps him from being further damaged. If you think the queen's dead and you warm her up, she comes back to life. The key for us as beekeepers, we can't tell that she's ever been heat or cold stress. There's no lingering effects. There's no, I mean, you could ask them, you could ask them, did you get chilled last night? But there's no outward symbol that these queens have been heat or cold stressed. But what was fascinating to me is this at low end, the high end, it doesn't continue to drop off down to zero. So there's some protective mechanism within queens, and we need to further understand that. But for now, we're just going to look in the colonies. So we've got, these are my control queens, and these are my heat stress queens, and we've evaluated a subset of them going in. This is, I think, about 7 or 8 queens in each group, to know that we've got the effect we want of reduced viability going into the field component. So now we've got 30 control colonies and 30 heat stress colonies, and 8 heat stress queens in these colonies, and they're all in the same environment. So we're going to test them through a Canadian summer and look at several factors. How are they performing? The first thing we were measuring was brood pattern. This is what I was talking about. This represents a square or 100 cells. That's 100 worker cells. And in this case, you're missing four out of 100. That's really good brood pattern. Over here, this is probably approaching 20% missing cell. That's the kind of poor brood pattern. And obviously this is even poorer. Hey, there's our supersedure cells. Look at them, 1, 2 on the face of the comb, spread apart. Those are almost surely supersedure cells. And in fact, I'll give a little bit away. Over the course of the summer, starting with 30 and 30, we lost 7 queens in each group. So once the queen was replaced, we took the colony out of the experiment. But we lost 7 in the control, and we lost 7 out of 30 in the heat stress group, or heat and cold stress group. So the first thing, this is summarizing the brood pattern effect, and in the controls, it was over 90% solid brood pattern. Here it's about, the average is this black line, it's about 70% solid brood. So that means 30 open cells here, if at above 70, 30 open cells. And I said 20 was my cutoff. 20 would be right about here at 80. But anyway, there's a lot of variation. Some had terrible brood patterns. Some had okay brood patterns. But look at the control. Look at the untemperature stressed queens. Those had really nice brood patterns. That's the first thing, brood pattern over the season. The next was adult bee population. And as you might expect, when you're missing that much brood, you're going to end up with fewer worker bees in the colony. So here on average, we had 20,000. This blue line is right at about 20, just over 20,000 bees in these colonies, whereas the temperature stress queens had about 10,000. So half the amount of workers present in those temperature stress colonies. That's pretty significant. And where is that going to have an effect? Well, you might have guessed it. So smaller colonies lead to smaller honey production. Here, this is in kilos, and this is near the Peace River area of Alberta. It's a good honey producing region, but 60 kilos a hive is really nothing for that region. But on average, those colonies in that apiary produce 60 kilos in the good colonies, the unstressed colonies. look at the amount down here. They produce on average 20 kilos in the temperature stress. Now, it's crazy. If you work in biology, I'm looking for my cursor. This kind of stuff drives you crazy. Look at this. 2 colonies that were great. 2 colonies over here that were really poor. That's why we have high replicate. We had 30 colonies in each group. If we'd done this with just 10 colonies in each group, it would have been all over the board. So you need good colony numbers to look at colony level effects. Lower honey production, which might be expected. But now the ultimate test, we're going to go into winter. Well, this is just summarizing all that. So we had, lower adult bee population, poorer brood patterns, and the honey production was reduced. Now we're going to go into winter, and we go into winter with 23 colonies in each of those groups. But remember, some of them are smaller. The temperature stress are smaller in general. So we go into winter with 23 each, and this is what we came out in the spring of the next year. We had 100% survival in those queens from fall to winter in the control group. Only 9 of 23, or 61% winter loss in the temperature stress group. Major impact on winter survival. It's actually not that surprising when you think about that those colonies were automatically smaller, not automatically. They were smaller probably due to this poor sperm viability. So poor brood patterns, reduced numbers of bees in the colony, poor honey production, and then poor wintering. Is there an effect? Yeah, there's an effect. There was a strong effect of poor sperm viability in these queens. And like I said, but don't go away from this thinking, as long as I keep my queens from getting hot or cold, I'm fine. It just also shows that the queen is vitally important to the productivity of the colony, and pesticides and other things can come into play. So high and low temperature both decrease sperm viability, not just high temperature, but also low temperature. And again, our upper range is 39 to 40 centigrade, and about 8 or 9 degrees on the low end. And all these things were affected, and I've already talked about those. So adult bee population, honey production, especially overwintering. So I closed by thanking Dr. Martha Zwarna and Steve Pernal from Ag Canada. They were the ones that did all the hard work. Project APIS-M in California funded some of the work, as did the Canadian Honey Council and the Canadian Bee Research Fund. Dr. Dave Tarpey, who I collaborate with a lot, collaborated on this study, as well as myself, and the National Bee Diagnostics Center there in Alberta, Canada, did a lot of the testing for us as well. So it was a group effort to show this work. And yeah, it did, again, colony level effects of poor queen viability. So we're coming back to this question now. What's the one thing that you can do to overcome queen issues? I can't really hear you, I'm sorry. It's a poor connection. So to me, the one thing as a beekeeper that I or you could do is to work with or select from or buy locally adapted stock. And I say this simply because when I've gotten stock from other parts, more temperate areas of the world, and tried to have them in cold areas, they don't perform as well. And anything that's gone through natural selection at the local level, whether it be in Germany, Scotland, Alberta, Canada, wherever it is, it doesn't matter. It's gone through and it has proved itself, and it's responded to the environment in that location. There's probably going to be a better queen and create better colonies. The other thing, if you're buying locally, you don't have to ship them. And we saw that shipping can be an issue. That's not to say that we don't need shipped queens, because we do. There's lots of areas of the world where we can't produce them. The other thing that I'll say is that done no work on shipping queen cells, but the queens in queen cells, when they're shipped or moved about, haven't mated yet. So you're taking that queen cell, placing it in your nuke, and it's mating there locally. So that queen cell should be fine. Just keep them warm. Anyway, breed from or buy locally adapted stock, I think is a great recommendation. Okay, I'm going to conclude with a little bit of sales pitch. Yeah, our April Monday flag behind us. So we had to move the UFA Russia meeting to 2022 because of COVID. And it's unfortunate, but we felt we couldn't hold it in 2021 as proposed. So then we'll follow that with a meeting in Santiago, Chile in 2023. two different areas of the world. So we hope that if you can join us in September 2022 in Ufa, Russia, you will, or if not in 2023, and you'll hear more about all types of things that are going on with bees and beekeeping. I will say that in Ufa, Russia, it is probably one areas of the world where they do this tree beekeeping, where they have bees in cavities within trees and they harvest from them. And it's kind of a unique style of beekeeping. So if you're interested in that kind of thing, please join us in Ufa, and hope to see you there. And with that, I'll close, and I thank you for your attention, and we'll answer questions if we have time to. All right. Thank you very much.
Right. Well, Jeff, thank you very, very much indeed for that. That was absolutely excellent. And as I say, we will be coming to a question and answer session, but first we'll be showing a short video of our sponsor from Thorn. Right. Well, thank you very much indeed for that. And thank you to Thorn for their generous sponsorship. Anyway, I'd like to say, ladies and gentlemen, is to thank you all very much indeed for being with us for these 6 webinars. And I certainly would like to thank not only Thorns, but our other sponsors for their very generous sponsorship over these 6 webinars. One of the very common questions that's been asked on this is, for those who maybe have missed a lecture, that can you see it again? And the answer to that is yes. We will actually be issuing links to a YouTube channel that the Ulster Beekeepers will have, and you will in fact be able to watch all of these webinars which have been recorded on that YouTube link. Now, we have still some editing to do on the webinars, so the actual webinars will not be available possibly for a couple of weeks. So what I would suggest to you is that you please keep an eye on the Ulster Beekeepers website, and we will in fact be announcing the links in due course. So please just bear with us for a little time. We have been really phenomenally pleased with the level of interest in these particular lectures, and this is the first time we have done this. So in view of that, I think that we will be looking towards doing this again in the future. I can't say when, but certainly what I would suggest, we will possibly do some more webinars at another time. It might be the autumn, it might be next year. But certainly we would ask you to keep an eye on the Ulster Beekeepers website, and we will announce them and we will advertise them as far as we can. We do have some contacts to many of you, so indeed I hope that this will help to make that process a little bit easier. So again, I'd just like to thank Jeff for that excellent lecture on queens, and certainly if we could maybe say start with some of the questions. If you bear with me now, if I could go to this. Let's see. Yeah, the first question is from Peter. It says, are queens which appear to have deformed wing virus genetically contaminated, and do they need squishing? Very technical term, that, squishing.
Good question. I actually have never seen one with deformed wing virus, so with a queen, but I would imagine that it might be prudent to take her out by whatever means necessary. Let me, before we go to the next question, John, I'll just say that it's a pleasure to be with you, and it's nice to see all the diversity of people who are attending. And I was monitoring the questions because we may get to most of them. Blame the drone, breed local, and good nutrition. That was, I saw a bunch of comments from different people, but yeah. So thank you to the Ulster Beekeepers for having me, and to Thorne for sponsoring it. Good to be here. Yeah, go ahead, John. Yep.
Right. No, as to say, yes, we did get quite a number of suggestions, and indeed quite a few of them were indeed quite right to exactly what you said. Keep it local. Anyway, the next question from Jim is, was there any difference in sperm viability between breeders who did open matings versus breeders using instrumental insemination? Okay, so good question. What I can tell you is that almost no queen breeder, well, none that I know of, use instrumental insemination to produce queens that they sell. The only reason, and I don't know why we talk a lot about instrumental insemination, that people do it, certain queen breeders and people doing experiments do it to make specific crosses. I would say almost without exception, queens sold across the world come from open mated. Open mated tend to be better. When they tried to develop a company in the US to do instrumental insemination of queens, the queens just weren't lasting very long. You can do it, it works, you can get specific crosses, but in general, instrumentally inseminated queens are for producing mother queens for certain things or to create specific crosses. So almost all the queens you're buying are open mated. Right, okay. Next is from Paul, and he said, would you expect America to have more queen failure than countries with less intensive apiculture and agriculture? Good question. I would like to know the answer to that. We did some work on transportation and transporting bees around the country, which we do in the States a lot. You lose a few more queens due to the transportation. I know that I was talking to some people in Great Britain, and they were saying they have 1, 2, and 3-year-old queens routinely. We do have queens that only last about 6 months. So we seem to be having maybe perhaps more queen problems. And why that is, I couldn't say totally. But it'd be nice to do some comparative studies to other parts of the world. I was in Australia and I saw a 4-year-old queen from one of the queen breeders, and that was amazing to me. It had a dot. We had a color dot on it. And that queen was still, it was one of his breeders. He was still breeding from it into the 4th year, which was impressive. Yeah. Yeah, I suppose indeed that question is quite topical, because you're going to have about 2 million hives sitting in California at the moment to pollinate the almond orchards. Right. Right. So the next one really is, are queens from swarm cells better than emergency supersedure cells or grafted cells? I don't know that there'd be much difference. I guess occasionally in emergency queen rearing, if they had very little brood to choose from, or they chose the wrong age, you might get a queen that was slightly inferior. But
in general, if the colony has selected and started to rear, whether it's swarm cells, supersedure, or even emergency queen cells, those are all queens are going to be pretty good. I did a quick and dirty experiment, and I let them do emergency queen rearing, and I weighed the queens. I thought the first queen out would always be the biggest. So I let them rear like 10 to 15 queens, and then I weighed them as they came out. And the first queen was not always the best. The second, third, or fourth queen was a little heavier, if weight is a good indication of queen health. So anyway, I think if the colony's deciding to rear that queen, she's probably going to be a pretty good queen.
Right, okay. If the optimum temperature for sperm viability is 25 degrees centigrade, why do bees keep brood temperatures at around 35 degrees centigrade?
So I wouldn't say that the optimum, we had that diagram, we were holding those queens at 25. The brood nest is at 34, right? About 34. It's not until you get to 38 that you start seeing a problem. It's because the brood, the developing young bees in the brood cells have to be maintained at that temperature. I saw some other flash up questions, so I'll kind of address it here. I think there are conditions in the hive in very hot climates, not on the British Isles perhaps, but in the Middle East and stuff, where the hive itself is having trouble thermoregulating. And so we might see a queen, or especially the drones that are hanging out on the margins of the hive, that could be suffering from heat stress in really hot weather. So, yeah.
Right. There's one here, actually, it is in relation to neonicotinoids in the UK. Just recently, our government is about to allow the restricted use of neonicotinoids to protect sugar beet yields. What recent papers, data, research would you recommend is taken into account when assessing the risk to our pollinators in relation to the exposure to neonicotinoids?
I can't list them all here. There'd be too many. No, there's a really good paper on the British Isles about proximity to canola rape, and the fact that there was more exposure in those areas where the bees to neonics, where they were near. And I've forgotten the first author on that one. Another good paper is by Williams, and it was in this presentation, where he exposed queens to neonics and saw some effects. The same by Lars Straub did drones and neonics and saw effects on drones. So there's a number of papers out there on effects of neonics on queens and drones in particular, or the whole hive. There's also one of the best colony level papers. I just call it the Swedish paper, and now I'm forgetting the lady's first name, but it was published in either Science or Nature in 2015 or 2016. And again, it was
Rundolph.
Yeah, I've forgotten her first name, but anyway, yeah. And Rundolph. And they were doing canola seed treated, not seed treated. And that to me is a very powerful paper because it was well done. They had huge hectares that they were planting, and there were definitely effects on pollinators.
Right, okay. Again, somebody, I think, just for clarification, what are the stains you use to test the sperm viability?
They actually, they can be bought from chemical companies. It's drawing a blank. Cyber Green, and I lost the name of the other one, right? It'll come to me in a minute and I'll say it out loud. You just have these two dyes, you mix them together and they stain the live or dead tissue differentially. Yeah, and I'm just drawing a blank on it. My access to my hard drive becomes, it slows down. I have a fragmented hard drive. The older I get, it be more fragmented.
Have you compared queens naturally selected by the bees, in other words, swarming, versus queens bred by beekeepers?
So I didn't say it in this talk, but I've said it in other talks. I think that we're selecting a little bit against survival. And I'm saying that because we select for gentleness, against swarming, which is reproduction, natural reproduction, and also then honey production. So honey production is, we can argue about that one, but these first two are survival traits. The swarming is reproduction, and gentleness. I mean, if we select them to be super gentle, they're not good at defending themselves. So I think I've always talked about local selection. I like a more wild type bee, and they're not as easy to manage sometimes, and they swarm and you don't get the honey production you need out of them, but they certainly can survive. So I think in general, as we've selected for these more specific traits, we've lost some of the wild type, and that's not, not necessarily a good thing.
Right, okay. This is from Robert. He said, could you give us the dimensions of the 100 cell template? I presume he sells masks, but I presume, I don't know you'd have that to hand by any chance.
I'll have to provide
my mind as well.
I'll provide it for you. It's also, if you notice, it's a, I forgot my geometry. It's a polygon.
Yeah, that's right.
I'll have to provide that. I'll have to provide
that's all right.
Yep.
Certainly, if you let us know, and as I say, even if the names of a few of the papers, we can put them on the Ulster Beekeepers website.
Yep.
Okay. What is your view of insulating hives to help bees keep a better all-over temperature?
Well, I think we, in many parts of the world, we underappreciate the need for insulation. We've kind of gone from a hive that bees in a cavity in a tree, and say in Europe, they had a lot of insulation in that cavity. And I think as we move towards these wooden boxes and things, that we're providing less insulation. So I think insulation and the moisture control are kind of critical. And then we get into all talks about the different hive designs, right? Which is the best hive design. But no, insulation is critical. And I'm in an area where I don't wrap the hives, but I do provide upper insulation. And I have a sawdust stuff that absorbs the moisture. So yeah.
All right. Again, it actually was again to do with insulation. Right. Okay. Well, it just says, really, could Jeff say something on drone fertility?
Yeah.
Have you got an hour?
No. I think I noticed a good friend of mine or a colleague of mine asked about that just before my talk today, and I said, well, of course we're the weaker sex. I mean, we are to blame for many of the problems. I did a quick thing on. I put these colonies in really hot environments in California, and the outside frames where the drones normally hang out got over 40 degrees, and so I think in some cases in really hot environments, the drones may be getting cooked, and then they can mate, but there's nothing there. I know that they're susceptible to pesticide exposure, and I say that even things like miticides, some of the miticides and things that we're using might be affecting drone fertility. So drones are fragile, and sperm, like in most mammals and other animals, the sperm is pretty fragile. So we have to, if you're cutting out drones for varroa control, which is not a bad idea, but in a natural setting, you have to make sure that there's plenty of good drones around. And I think the weaker drones, if they've been infested with varroa or whatever, they're going to die out. They're not going to mate with the queen. So only the natural mating system, only the good, healthy drones are going to catch that queen and mate with her. So there's a process of elimination perhaps with the drones, which is good.
Right. Does it make a difference if you make queens through doing splits so as they have to make a queen, please?
Yeah, I hear people talk a lot about, there's a word in the US, they talk about walkway splits. So you make it and make them do emergency queen rearing. You just want to make sure that there's enough young brood in there that they can select from. The other thing, when you make a split, if you don't have enough young bees in there, they're just maybe not going to raise the best queen. I'll tell you what I like a little better is I like to learn grafting and queen rearing. Graft from your better queen and raise a bunch of queen cells, and now make your splits and put a queen cell in that split, and you'll be further ahead, and you'll have a better, you control the genetics a little bit, things like that. So it's not that making those splits and making them raise the queen is going to be bad, but I like to select from my best, and I use queen cells to make nukes with. Right.
Okay. Are there commercial solutions for regulating heat when shipping queens on the market? So I presume that's regulating heat for the for the bee packages?
Yes, there are some people working on it. I was contacted by some people in Sweden, and they're working on it in Sweden. I did some work on moving air within these queen packages and heat and cold air. I'm not a business person, so I'm not going to develop it. And I know a group in Canada that are working on it as well. So I do think there's probably a market there. We ship organs around the country and keep them at nice temperature, and we ship baby chicks and stuff. We could figure out a way to ship queens and make it guaranteed arrival. But there's a little bit of engineering that goes in there.
Right. Okay. I'll actually think really have to make this really the last question, because Jeff, you've been very good here, but we've had a very good selection of questions, I have to say. But I'm going to make this the last one. Would drones from a laying worker have the same amount of sperm as a drone from a fertile queen?
That's a very good question. As a scientist, well, we're supposed to know when we don't know something. I don't know the answer to that. I have to suspect that if that drone was reared well enough and fed well enough, that he could develop, reasonable sperm. So I don't think it would be anything in particular that he would be necessarily inferior. But,
right. Okay.
So
right. Well, again, really, thank you very much. I'm actually just going to make one very short announcement. A lady called Anne Robury, who is from the British Beekeepers Association, and she's just saying, or would like me to mention, that they're having an Asian Hornet conference on the 6th of March. So if you can get that through the BBKA website. Okay, thank you very much indeed. And Jeff, as I say, thank you very much indeed for that great lecture. And if you hold on for a few minutes, I'll have a chat with you when at the end. And again, really, ladies and gentlemen, thank you very, very much indeed. And keep an eye on the Ulster Beekeepers website, and we will be making links to these lectures, but also hopefully for future webinar series. So thank you very much indeed for attending, and good night.
Hope to see you in person soon. Yeah.
Indeed. Yeah, that is true. Hopefully we'll have a conference next year, face to face, we hope.